All right, Gen Chem kids, we are going to talk about nuclear fission today and nuclear fusion a little bit. And we're going to talk about also how nuclear, basic nuclear reactor works as well. Okay, nuclear fission. Fission, remember, means breaking apart. The opposite is nuclear fusion. Fusion means to put things back together. So the first nuclear things that we discovered about a little over 100 years ago was fission. Big, huge atoms that were so large that they were unstable, that they were breaking apart. Okay? The evolution of energy in nuclear fission is directly related to a decrease in the mass that takes place of splitting a more massive fissionable atom. So we are splitting atoms into two less massive atoms. So I'm taking a big atom and I'm bombarding it usually with a neutron. Okay? And as that neutron goes into the atom in that nucleus, because that nucleus is so large, it's unstable, that nucleus kind of splits it in two. So I will get two smaller atoms off of that reaction. Now, these two smaller nuclei are not necessarily stable. It really depends on where they are on that band of stability. Now, as the atom splits from this bombardment of the nucleus, it is also random how it splits. So I can get lots of different combinations of two nuclei. I will also usually get a couple nuclei coming off of that split as well. Or not nuclei, neutrons off of that split as well. So just like if you've ever played pool and you set it up, you put all the balls on the front and you take the cue ball and you hit it, where those balls go is kind of random depending on where you hit that cue ball with. So we will get different combinations of different elements as we hit that big initial atom. Okay, so this is how nuclear fission works. Okay, so this is just a basic way that we think of it. And there are only a few radionuclides that are fissionable. Uranium-235 is one of them. Okay, if I bombard a nucleus of uranium-235 with a neutron, for a split second, I will get uranium-236. Now, uranium-236 is incredibly unstable. So it will break apart and it will give me two smaller nuclei, two smaller atoms, and it will usually give me a couple extra neutrons in that breaking apart. Okay? Now, a lot of times it will break down into barium. You'll also see, barium is 56. So you would get 92 minus 56 would be 46. So you would get palladium here. Palladium would be our smallest. But once again, barium and palladium are not necessarily what you're always going to get, but this is a very usual combination. When we see these splits, we will get kind of a distribution where we do get some elements more than others, but we do get a range of elements when those two nuclei split. Okay, here's another example. Now, this next example goes on this premise, these neutrons that are released in this split. What if I have another uranium-235 that is really close by and these neutrons hit that? This is what happens when we call it a cascading reaction. So here we go. Let's look at a cascading reaction. So here I have a uranium-235 and I'm hitting it with a neutron. and it splits into barium and krypton. Okay? And I get these 3 more neutrons right here. And if I have more uranium-235 that is near enough that these neutrons can hit those nuclei, those will also split as well. Now, this is kind of misleading in that it's always giving us krypton and always giving us barium. That's not really the case. But these nuclei get hit and split again and give us 3 more neutrons each. So now instead of 3 neutrons, we now have 9. What if I had more uranium for each of these to hit? Could I get 3 more neutrons for each of these? Do you see how quickly this cascades into a reaction that would create quite a lot of nuclear reactions going on at the same time? Okay, so this is what we call a chain reaction. Okay, because one reaction will set off another reaction. And notice how this chain reaction just grows exponentially. So I started off with 1, then I had 3, then I'm going to have 9, then I'm going to have 27, then after 27 I'm going to have 81. We get this exponential reaction going. So it quickly goes out of control. Okay? And this is the reaction that they used to create the bombs that they used on Hiroshima and Nagasaki. So one of the bombs that they used was based off uranium-235, and the other bomb, that was the one that was on Hiroshima. So, and then the bomb that they used in Nagasaki was based off plutonium, which is also fissionable. Once again, they both are chain reaction bombs. So they had to have a critical mass of uranium where the uranium or the plutonium was very closely packed together so that the neutrons that were coming off of these reactions could go and in turn hit another nucleus and have that react. So what they had to have is very concentrated, closely packed uranium and plutonium to have that go together. Now, what happens if I don't want this reaction to go out of control? Can I control it? Is there a way to stop these flow of neutrons? Can I stop these and maybe just only let one at a time through instead of having it cascade into this huge chain reaction? I can, and this is how we do it in nuclear power plants. Okay, so nuclear reactors. This is a diagram on a nuclear reactor. Let me put this up here. Okay, so I don't know if you've ever driven by a nuclear reactor. Probably the one that most Utahns would probably have spent time driving by would be the one in between San Diego and Anaheim, California. If you've ever been down to Disneyland and been in the San Diego, Anaheim area, if you drive in between those two cities on I-5, off to the left or well, if you're going north, it's off to the left. If you're going south, it's off to the right. Off to the west, you'll see 2 big, huge cement domes in the middle of the Army Reserve or the Army camp down there. And those 2 big domes off to the west, off of I-5, are actually nuclear reactors. And so you'll see those if you're down there. Our nearest one here to Utah is actually not that far away. It's up about 4 hours north in Idaho Falls. There are several nuclear reactors there. In fact, the first nuclear reactor that was ever used for community electricity, to create electricity for the community, is actually now a museum up there in Idaho Falls. It's called EBR-1, and it's just outside of Idaho Falls. You can go and tour the museum. It's actually a really cool little museum. Okay, so this is how they work. We will have inside the nuclear reactor. So let's focus on inside the nuclear reactor really quick. So this is a small diagram of inside a nuclear reactor. We will have the rods of uranium or fuel, and those are these black rods right here, okay? And they usually use uranium. Sometimes they will use plutonium, but they usually use uranium-235. And then they will have control rods. And the control rods are movable. They can move these rods up and down. And they can move these up and down depending on how much electricity they want. So the further down these rods are, they're shutting off that chain reaction. They're not letting the neutrons get to the next nucleus to break it apart. But when they pull those rods up, they're allowing those neutrons to get to the next nucleus to break it apart. So the more the rods are up, the more electricity they can generate, the more heat they generate. The more those rods are down, the less they are generating and the less nuclear reaction is going on. Okay, so this is what is happening within the reactor. Okay, and they control the reactor with those control rods. And the control rods are usually made with cadmium because cadmium can absorb a lot of neutrons. They sometimes are also made out of nickel. So it's usually a cadmium-nickel blend, mostly heavy on the cadmium. Okay, so let's look at this. So here is a simple diagram of a reactor. This is the core, what we call the reactor core, where we have the control rods and we have the nuclear fuel. So we have the nuclear fuel and the control rods, and within that, we are pumping in, we have a pump right here that is pumping in water. We are using the nuclear reaction within that reactor core to heat up water to generate steam. And we are creating steam right here. Notice this is a self-contained loop of water. We're taking that really hot pressurized water to put it in the boiler. This is what we call the boiler, to make steam. And that steam will expand and go up through this pipe. And once we put it through that pipe, that pressure from the steam turns a generator. So we have a steam turbine. So this is pressure from the steam that will take that turbine and turn it. If you've ever blown on a pinwheel, the pressure of the air going from your mouth to the pinwheel will turn the pinwheel. And we have that turbine rotating in the middle of a bunch of wires. And that bunch of wires, if we have a magnet, it's a magnet that we generate and we turn in a bunch of wires, it generates an electric current. So we have an electric generator. So we have a magnet that we turn to create an electromagnet that creates electricity with this pressure from the steam. And this will go off to the electrical grid. So this is where we have the electrical grid. Oh my gosh, that's horrible. Let's erase that and let's try to write that better. The electrical grid. So that electricity is now part of the electrical grid, and it is handled just like any other electricity that we would generate either from coal or for natural gas or anything like that. So that's gone off to the electrical grid. Now the steam, we want to reuse this steam. So what we want to do is we want to cool it back down so we can put it back into the into the nuclear reactor and generate it all again. So what we have is a condensing tower, and we call it a condenser. Okay, we usually have nuclear reactors hooked up to a pretty large body of water, whether it's a lake, a really large lake, a river, or an ocean. Okay, we will take that cool water from that body of water, that river, that ocean, that lake. We will pump it into this condensing tower. And that cool water will take the steam and cool it down into water again. The problem with that is it releases warm water back out into the river or the lake or the ocean. And that is what we call thermal pollution. And many times this warm water that we release back into that river or ocean or lake is too warm for the aquatic life that lives in that area. So it actually ends up killing that aquatic life. A lot of times that water is so warm that it won't hold the oxygen in the water that the aquatic life needs. So the aquatic life actually ends up suffocating because they don't have enough oxygen in that water to breathe. So that area where the warm water comes out of the nuclear power plant is usually a dead zone because the aquatic life cannot live there. But on the plus side, none of this, as you see, none of this is generating carbon dioxide. It's not generating greenhouse gases. So, and we get a lot of power, a lot of power off of this compared to burning coal or natural gas or any of those things. This will give us thousands of times more power per amount of fuel that we use. So there are definite trade-offs between nuclear and conventional power here. Okay. So this is how things are done within a very basic design. There are different designs of nuclear power plants that do use different things here. Notice that this core here, let me get another color. This core is surrounded by a confinement shell. This confinement shell is usually made up of reinforced steel concrete. So we have steel concrete shell here. And we want that steel concrete shell because if we actually have a leak of radiation in here, we want that steel and concrete to be able to shield whatever nuclear spill that we might have and hopefully contain it so that it does not poison the environment. Another thing is we don't always use a river or a lake for this. I don't know if you've ever watched The Simpsons, but on the intro to The Simpsons, they have this huge tower. Oh, wow. That kind of looks like this shape where Bart works and they have smoke or steam coming out of here. Those are what are called cooling towers. And they will take water from a river or lake and they will kind of do a condensing like this, but they use a huge tower instead of just this little apparatus to do cooling. So there's lots of different designs out there. Okay, last but not least, we have nuclear reactors, and all of the nuclear reactors that we have in the United States, and in fact the world, they are all based off of this. They are all fission. But if you remember from our binding energy diagram, fusion, where we are putting hydrogen together to make helium, gives us a lot more energy than breaking uranium apart. So the energy world right now is really trying to figure out fission, or not fission, fusion. So this is the design that they have of a fusion reactor. And we do have a fusion reactor. We have a couple of them in the world. Probably the most active one is out of California Institute of Technology in California. They've been able to do fusion reactions, but the problem is they have to put so much energy into the fusion reaction to get it to go that they don't get enough energy out to make it worthwhile. So it's really still in the theory and the testing stage, but this is how they do it. Now we know that fusion happens in the sun. And in order for fusion to happen, we have to have incredibly high temperatures and incredibly high pressures. Temperatures to the point that we are at about 10,000 degrees Celsius. I don't know about any material on the face of this earth that can withstand temperatures that are that hot. So in order to get temperatures that are that hot, they have to use magnetic levitation to levitate the plasma within this central solenoid. It's kind of a big donut thing. And they get the plasma moving super, super hot and fast, going around this ring, getting it to be really, really hot. But they've got to levitate it in this donut-shaped thing in order for it not to touch the material that the solenoid is made of, so it doesn't melt the solenoid. So in order to do that, that's a lot of energy, okay? And they will then get enough pressure and enough temperature to actually have plasma, which is our fourth state of matter. We have solid, liquid, gas, and plasma. And we normally don't talk about plasma because it's superheated stuff to the point that the electrons leave the atom. We really just have neutrons and nuclei left. And the nuclei, when we get this hot and this much pressure, will start fusing together and make the fusion reaction happen. But as I said, so far, in terms of practicality, this is not practical because we do not get as much energy out of it as we put in. They are still trying to figure out how to get this to work. So I have a little Ed puzzle for you that goes over nuclear and the pros and cons and what's going on with nuclear within the United States. Just to let you know, within the United States, we have not made a new nuclear reactor for the last 40 years. And our electricity grid, if I can speak, our electricity grid is actually very antiquated here in the United States. We do need to figure out new energy. Now the question is, are we going to continue our old ways and use fossil fuels and continue burning and creating greenhouse gases? Or are we going to start using a new profile and use renewable energies and maybe even bring nuclear a little bit more back into the mix? That is the question that we need to figure out as a country. So this Ed puzzle kind of gives you the pros and cons of what's going on with nuclear. I want you to listen to it and do some research if you want, and make up your own mind about how that works and how you would like that to see in the future or not. All right, have a great day and have a great UEA. We'll see you. Bye.